13. Let's see. This is me, Sean OMeara. It's my email, Twitter, in case you're into that sort of thing. Actually, that's my email because we just renamed the Mops Code to Chef. So now I have that email. Who am I? Why do you want to listen to me talk about configuration management instead of somebody else? Who am I? I have been a systems administrator since I was old enough to type. Right? I remember I was the only one in second grade that could load the floppies and stuff. Start with the Dewey House processor. Right? Cut my teeth in Linux land, somewhere around Slackware. I've an expired NT4 MCSE. I've been doing this for at least a couple of years now. So that's me. So I think the hardest part for me actually is trying to cram all this stuff I'm going to say into an hour. So I might talk fast, maybe. If I'm talking too fast, somebody just tackle me. Right? Just wave your arms or yell at me, like, slow down, please. Because I tend to do that, especially after I drink lots of caffeine, like I did this morning after the beer thing. So let's get started. We're going to start at the very beginning. Right? The dawn of configuration management. Right? So we're going to talk very, very abstractly for a little while before we start getting into more specific things. We're going to say what exactly is configuration management. In general, it's strategies and techniques for managing configuration and its complexity. That's it. That's all it is. And then beyond that, it's the art of change management going forward with your infrastructure. Okay. So once upon a time, we started out like this. Right? This is the monkeys around the watering hole. Right? This is how we all started out. This is intuitive. It's super, super, super intuitive to manage things manually. Right? This is kind of how we interact with the world. We log into a machine and we manipulate it with our fingers. Right? This is honestly kind of still how I manage a lot of my laptop. And so do you. Like, how many people are writing config management on their cell phone? Right? I mean, I'm sure there's some TF Engine guy in the back. Be like, oh yeah. But everybody else is not. So make with the clicky, you know, like log in to the web server or web page and do the things, right? Like super intuitive. Stop doing that. This always feels the safest. People that are, especially people that are new to config management, they always want to do this. Like when the website breaks or whatever, they're like, shut the config management off, and then they like want to log in and do things manually because it feels safe to do things manually. This is an illusion. Stop doing it, especially if you have a lot of machines. Trust your config management system. Learn how to actually wield it properly. Okay? So manual configuration, we stopped doing this. Why? It's labor intensive, it's error prone, it's difficult to reproduce things, and it's obviously unsustainable. So stop doing things by hand. So from there we evolved into scripting, right? Natural kind of evolution. Everybody in this room has written these programs. Every single last one. Right? So you boot a machine, you install your operating system, right? Like you have base, Debian config on there, base whatever. Then you go and set up. Right? This takes it from the beginning all the way up to, you know, like a working web server, or database, or index, or you know, whatever you have. You've written this program. But then what? You write these programs. Right? Just do this, do that. Everybody's written them, right? Sometimes you put it on a for loop, sometimes you just test it with other machines. This is better, right? It's a step in the right direction, but ultimately it's ad hoc in nature, right? You're going to lose kind of the history of what you're doing unless you're constantly adding the contents of like doit.sh to your setup.sh, like you're going to end up losing your shit somewhere, right? So, stop doing this. Lacks a good testing methodology other than kind of like a manual, like feels good sort of test. Like doit.sh to like a canary machine. Right. Then we moved on to this, right? File distribution. Everybody loves file distribution. This is where we actually come to terms with the fact that we're dealing with distributed systems. Okay? So we've all done this, right? NFS, the network is the computer. Right, so we've all set up an NFS share, and we'll like stick our like bin like files over here and do this. We'll mount directories and blah, 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 blah. That's great until you have a network partition, and then suddenly, like, all your computers lock up, right? SMB is a little better. AFS, SSHFS, like, you get the idea. All kind of the same thing. Then, if you're a little bit more enlightened, you'll move on to these sorts of things, right? We're going to use like FTP, TCP, various protocols that actually move files around from one computer to the other. But at the end of the day, you know, it's still like it leaves some things to be desired, right? You want to update your config somewhere, push it out. How do you restart your service? Right? You got to fall back on to other things. So this is a little bit better, and you start to see elements of like all this historical stuff like in the modern techniques too. Right? So like we still copy files around, for example. But you know, like we're still kind of back in the Stone Age with this. Put a star next to the SCP on the cron here because this is when we first kind of realized we need a control loop to kind of keep things in the state that we need them. You'll often see this sort of thing like, oh, I'm going to pull from this HTTP server on a cron. Pull is better than push. If you disagree with that statement, you are wrong. So then we moved on to execution management. Right? This is still very, very popular. Image management, so you play a machine, right? You start with your base state. Everybody does this when they got their shiny new VMware cluster, right? Like, let's make a machine, we'll snapshot it. We'll try to deal with, distributing those images as artifacts. Not the best in the world. Containers, special case of this, still ultimately execution management. Which isn't to say it doesn't have value, but it is at a high level a configuration management strategy that you can use. Okay, not mutually exclusive with what I'll be talking about later. Then for the distributed systems version of this, you have SSH on a for loop. Everybody's written that script as well. For in backticks cat servers.txt do SSH root at $I do it.sh. You've all written that. Func commands and message queues. Still super useful. I think I might be the only person in the universe that actually used this program in production. It's called ISConf. Really interesting. It basically keeps a journal of the root commands that we type and plays them across all the machines in the ISConf domain. It's kind of an artifact of like the config management wars from like the Usenix style, or the Usenix era of this sort of thing. Very interesting, good to check out if you're into like config management history, like I am. But ultimately, it has kind of the same problems as a lot of the other techniques, right? So loss of history, image sprawl, right? You're dealing with, you have 17 different kinds of servers. You're going to have 17, at a minimum, kinds of like image artifacts, like Docker IDs or whatever you got floating around the place. But however, it is kind of easy to like manage change like across nodes if you have an external guy with like an SSH infrastructure. Like, you do this, you do that. We'll get to that later. Then finally, we get to this. Right? This kind of came from outer space and landed in Oslo, I guess in the late 90s. And this is kind of where we're at, right? So, I don't know if you can see this with the light, but there's Mark Burgess. There's us. Yeah, we're all kind of like huddling around the monolith like that. And it's telling us something, right? And we're building tools with our newfound knowledge that came down delivered from space, right? So this talk is going to be, everybody likes to like compare these things, like how are they different? Right? I'm going to talk about how they're the same. Okay? So I'm going to talk about CF Engine. I'm not going to talk about bconfig because I don't really know anything about it. I'm going to talk about Puppet. I'm going to talk about Chef. I'm going to talk about Salt. I'm going to talk about Ansible. It's all in and out. So I'm going to talk fast. Okay? So here we go. Let's do this. So part 2, policy. So at the highest possible level, right? So modern config management is about describing policy. right? So what is policy? It's stuff like this, right? Etsy password should be mode 0644 and shadow should be mode 0600. This is the very first thing they teach you in Unix class, right? It's like, how do you log into the machine? Username, password. This is the next thing they tell you, right? The password database needs to be protected, right? Seems like a pretty good policy to enforce, right? The permissions mode on your password database, right? So we're going to put that in our policy, right? It's the kind of thing you find in like military security guides, right? Make sure you do this. And these sorts of things pop up a lot, you know, like we should have this user, they should exist and be in this group, right? Kermit, Fonzie, and the Muppets all hanging out in the system. Then you start seeing, once you actually want to run software on your machines, make them do useful things, you start installing packages, you start configuring your clocks. All this is very familiar. It's policy, right? This is what the machine should be doing. Sometimes it's not as easily translatable as this. You kind of get like a little more hand-wavy where you start talking to your Java devs like, we need this JDK installed on this web server, and does all this stuff. But at the end of the day, policies. And the important thing here is policies are declarations about the state of things on the system, right? So vocabulary word, declaration, state. Policies are applied repeatedly and repair the system when needed, okay? So this is important. There's a notion of control loop that comes into play here, right? You can't just like do stuff to a server and walk away. That's not management, right? You have to revisit it every now and then to make sure, like, you all right? Right? Sometimes people log into it and do evil things and repair it. Right? So policies are applied repeatedly. Policies often change. This happens a whole lot, right? Let's say I'm working for WidgetCo, and we make a piece of software called Widget Factory, right? And we sell it. And so I'm going to want this version of Widget Factory installed on all my systems, version 1.2.3, okay? Well, there's a new release, they artifact version, and now you want to install 1.3.0, okay? So there's an example of policy changing and that need for the control loop to come in and actually manage your system over time. Repeatability. So, are we convinced that we want to repeat our policy? Yeah. So, in our quest for repeatability, we start seeing words like this. So, idempotent, convergent. Since y'all gave me a soapbox, I'm going to go ahead and stand up and say, stop using the word idempotent wrong, because you all do. Like, pretty much every time you say the word idempotent, you mean convergent. Okay? I'm going to show you the difference. So scripts in general, generally not repeatable. Okay? Here's an example of a non-repeatable script. So I'm going to boot Debian, right? I'm going to run my script. So what happens after I run the script for the first time? I have a working DHCP server. Right? What happens if I run the script a second time? Broken DHCP server, right? The reason is because the script is not safe to repeat. Okay, so I'm actually like concatenating data into a file here. So I'm truncating a file, or I'm not truncating a file, concatenating. This is an example of a non-idempotent function running the script. Okay. Likewise with this, right? I'm going to set up the initial state. I'm going to actually put some data into a file here. And I'm going to run two non-idempotent commands that you'll very often find in shell script, like a sed, right? So the first time I run the sed, it's going to mutate the string, right? It's going to dig out this dog and replace it with dog, right? The second time I run this sed command, I get an empty string, right? So another example of a non-safe to repeat function that you're applying to systems, right? So, what? So, but they can be, right? Scripts can be safe to repeat. They totally can. But you have to write them with this in mind. So, here's an example of an idempotent operation. Okay? This is idempotent because it's truncating the file. Idempotent just means that you can apply the operation an infinite number of times and you will always get the same results. It says nothing about having to actually do the work or not. Okay? To similar, very closely related concepts, but they're different. And we need a word to describe each of them, and we have them. And the word idempotent is this one, right? And convergent is the other one. And I'll show you that in a minute. So stop it. Stop saying idempotent. So I'm going to prove that it's idempotent, right? So I'm going to write this data to a file, and I'm going to run the script over and over and over again, and I'll yield the same output. Okay? Safe to repeat, idempotent operation. Okay? But the problem is I'm doing the work every time. So idempotent good, but it's not good enough. Right? So what we actually want is convergent operations. Okay? We want this test and repair behavior. Okay? So I'll talk about these kind of in depth. Convergent operations, test state, and repair if needed. So here's my repeatable shell script. Can't really see the red lights on too well, but it's not really you'll see here it's just test and repair. Right? So at the top here, I'm running a test, querying my RPM database, and then, depending on the output of that test, I will take action to repair the system. Right? Test and repair, test and repair, test and repair. If you squint your eyes a little bit, you'll see 3 blobs of code on the screen. Each one of those is a convergent, right? So 3 convergent operations. Likewise with HTTP, HTTPD, same kind of thing. It looks almost the same as NTP. This is a pattern, right? So we're repeating this pattern across 2 things. So we have NTP and HTTPD, both things that you can install from your Linux distribution's native package management system. Very often you can get away with this pattern. Install the software, write the configuration, start the service. Right? Very common pattern. It's probably the most commonly encountered pattern you'll ever see in config management. Package template service. So, and then finally you have this control loop that runs and repairs the system. Right? So each one of these little operations, each individual thing needs to be thought about individually, and it's on a controller. You end up with this. Right? An autonomous agent fixing the system on a controller. The bug should be closed. So, let's talk about convergence. This is always fun for me to explore. You always find something interesting when you go digging around in convergence land. So this is pretty easy to crack, right? Convergent operator on a system repairing the state of the system. Just one. Pretty easy. Well, what happens when you put 2 on a system? Right? What happens if they have conflicting policies? Okay. What if you have one convergent operation starting a service and one stopping a service? Okay. What happens if you have a lot? All kind of running on the system at the same time. Right? This is how you need to think about config management code, right? A swarm of these config management, or a swarm of these autonomous agents kind of like infesting your system and like repairing various parts of it. Okay. If you have this in your brain while you're writing your config management code, you will win at it. Right? So, what time is it? About halfway done. You guys want to see something cool?
Yeah.
Alright. So I wrote you a new config management language in Bash. Because Bash is the lingua franca of DevOps. And so if you want to check it out, you can go here. It's on GitHub because I put things on GitHub. So this is what we're going to do. We're going to start out. I wrote a script called how status. Right? It's basically an integration test script. It's going to check, parts of the machine, see if they're the way I want them to be. Okay. So this is what happens when I run how status. How looks at various things on the system, groups, users, a directory, and the presence of a file. Right? And it says they are all broken. Right? Everything I wanted to test about the system has failed. Right? So what am I going to do? I'm going to write some bash. So I'm going to do this in like 4 slides, by the way, so don't be scared. So the first one is I'm going to take 2 convergent operations and put them together to form a type. Okay, so test and repair. Test GPT ENT group type awk. Do some grepping. Yeah, we find it. Okay, repair. Test and repair. Test and repair. Right. So I've made a group type in Bash. At the top, defining what my variables are doing. So I'm actually creating an interface. Right. So I have 2 parts: interface and implementation. Test and repair. Test and repair. Okay. Second one, user. More of the same. Okay. Test and repair. So I have 1, 2, 3, 4, 5, 6 for a total of 8 convergent operations now. Making a user. So again, at the top, interface and implementation. Right. Very easy stuff. You know, it's just running the user mod command. Okay. Finally, for a directory, I use 3 more. Total of goes up to 7, 8, 9, 10, 11. So again, interface implementation. Right? Set some variables, do something with them. Right? Test and repair, test and repair, test and repair 3 times. And then for my last one, actually turns out CP-U is actually convergent, so I didn't really need to do that. It does it actually under the hood. So a total of, am I at 12? Configure 4 types, 12 configured, 12 convergent operators, all on my system working to repair the machine. Okay, so I've written my functions. Let's consume the functions. I'm going to actually write some policy now in Bash. So I'm going to say group space. Give it a parameter, HAL 9000, 2001. Does this look familiar? So, cool. I'm going to run that. Repair HAL. And it's fixed. That's good. But I don't actually trust the machines because I'm kind of Luddite, so I'm going to deactivate HAL. So he's offline. Good. Stay offline. Robot. Want to do something really cool?
Yes.
What happens if we do this in the wrong order? Huh? So we're going to do unordered repair. How? So I'm going to do this the exact wrong way. Okay? I'm going to first try to update a file and put it in a directory that doesn't exist yet. Right? I'm going to create the directory and give it an owner and permissions of a user that doesn't exist yet. Right? And then I'm going to make a group, and that, well, I guess that'll work. So let's run it, see what happens. So I'm going to run my policy, and look at that. It actually fixed some of them. Right? So I have stuff at the top, actually online. The user actually failed to create. The directory actually exists, but it has the wrong permissions, and the file has not been copied yet. Second iteration, right? More of it is repaired, but not all of it, right? We still have, it looks like the directory permissions have not yet been repaired, okay? And then third iteration, I finally converged to the state that I want my machine to be in, right? That is convergence in action, test and repair on a loop, okay? And that's kind of like the lizard brain of configuration management right there in Bash. So, does order matter? Well, obviously it does not, because you just showed me that, Sean. Actually, it does. It matters a lot. It matters a lot. You end up in situations where, you know, like you're mounting file systems and disks and changing like the actual like view of the system and like starting services and packages and all these things. All of my operations actually were like super low key, right? They were doing very specific things. Sometimes config operations actually have pretty big side effects on the system, and you need to watch out for them. So there's that. And here's a question: what would happen if I actually went into my type of implementations, like my user, and rearranged all of the functions in the files? If I went into the group in the user thing and actually reversed my test and repair things and ran it again, it would converge. Because the system's, the system is, it's going to stabilize because there's no conflict in the set of convergent operators that are happening. Right? There's nothing fighting with each other. Right? called system. No, I don't know. So yes, order matters a lot. So write your things in the order that you need them, especially inside of like type implementations. So, yeah, gonna jump into. We're gonna wrap about promise theory for a little bit here. 1127. So this is kind of like what the monolith dropped off when it like landed, right? This is promise theory stuff. This is kind of what binds all this stuff together. So real quick, agents are autonomous, right? Each one of those little boxes, the test and repair loops, they're autonomous, right? They are their own little things. A promise is a signal or message perceived by an observer. Okay, so within a set of these things, they can actually look at each other and see what's going on. That's how they can cooperate. Okay, promises may or may not be kept. Just a fact of life. Right? Sometimes machines break. We need to account for this in our system. Right here, agents can observe other agents. Right, this is how you can restart services when config files are repaired, things like that. Right, agents have local information. Very important. It has a star next to it. This is the implementation of an agent has all of the information that it needs to repair what it's concerned about. Okay, so like a user's agent knows how to manipulate Etsy password on Linux, and knows how to manipulate the Windows database on Windows, right? It knows how to do everything it needs to do to actually take care of itself. It's also important because it's why dry run mode cannot work properly, right? You can't, like, they only have local information about themselves. They can't see what other things are doing on the system in a real run mode, right? You can't like query one of these agents and be like, hey, what are you going to do later after these 15 other agents have popped off, right? It just doesn't work. If you want to know more about that, get me after this. And then the inner workings of agents are assumed to be unknown, also important, right? This is what lets us build black box providers, right? So I can implement a provider in like Bash or assembly or C or Go or whatever, but it's behind this interface. I've walled off the implementation of the agents. You're not allowed to know what's going on under the hood, right? So agents have intentions, possible behaviors, things that they can do, right? Package agents can typically promise to install a package or uninstall a package. Users can promise to be present or disabled. And then agents can make assessments about other agents on the system, right? So they can observe each other, send each other signals, okay? And then configuration management tools embody tenets of promise theory intentionally or not. And it turns out that the current crop actually do. Like the current crop that's like derived from CF Engine, like they all kind of do this, on purpose or not, okay? So domain-specific languages, very popular thing to talk about. What do they do? DSLs, this is all they do. They restrict the machine instructions that you're running to convergent operations. That's it. Right? So they don't let you make non-idempotent like statements unless you're abusing the exact statement, and if you're doing that, stop. Right? And then they also manage ordering. Okay, the different tools have different philosophies about ordering. CF Engine will actually order by type, right? And then it'll actually apply a number of times to take advantage of that convergence thing I showed you with the bash scripts. Puppet sorts a graph to determine ordering. Chef just does what you tell it to, and then Salt and Ansible kind of do that as well. Only they kind of like spray these things at machines instead of pulling in. So here we go. Little CF Engine policy here, right? So I'm going to install Puppet, CF Engine, right? But we can actually look at them and see that indeed we have a type, subject, and then a number of intentions that this package type, this autonomous agent that knows how to repair packages can intend to do. Okay? Puppet. So again, type, subject, intentions. Okay? So we have a package type that knows how to ensure that packages are installed or disabled. Right? Here we have a signal. The agents are observing each other. Right? This one's notifying service to restarts. Okay? Chef, install some salt. Okay? Again, package, subject, intention, exactly the same. DSL doing the same things across all the languages. Okay. Again, observation, right? Agents observing each other. Right? So the service can actually subscribe to the template to see if it gets repaired. I need to restart the service. Okay. Here's some salt. Again, type, intentions, subject. Right? And then Ansible. Again, same stuff. Right? Monolith speaketh. Right? So we have package type. It has a subject, and then it's going to say it's. I intend to make sure that this is its latest version. Okay. And then again, signals. Agents can observe each other. Wire word. So that was exhausting. I'm gonna drink some water. Here's a basket of kittens. And we're back. Okay. Part 3. Composition. Let's write some chef. So, chef is my native tongue, so I'm going to speak it if you don't mind. So, recipes. Okay. Here's a chef recipe. Pretty freaking simple. Right? And now that we just got done talking about promise theory and autonomous agents and all this fun stuff, like, you will see what it does very easily. Okay? So I have 3 resources. Again, that same pattern from back at the beginning of the talk, package template service. Okay? I'm going to install the software, make sure that its configuration file looks correct, and then if that needs to be repaired, I can restart the actual service. Right? Feed this into a control loop, gives you a vector to actually change the state of the system by updating the policy, right? So I can change the template, source, or the inputs, and actually make the service restart, right? I group them together into a body of testable intent, okay? So the recipe where order matters, you put them together, and you can actually test them, which is great. Testing is a whole different topic that I can talk about for days and days and days. I'm not going to go too far into it, but do it. Because we're writing software, frankly. So I make my recipe, I compose it with 3 resource statements, and then within Chef I can refer to it like this. Right? So I'm saying I want the recipe and the HTTP cookbook named server. Right? It's kind of like a chef-ism. So pretty easy. I'm referring to the source then in my template. Right? So I'm saying autonomous agent. I want you to write this file, but I want you to use this template source. Right? Well, I need to put that somewhere. Right? So I now have a cookbook. Right? So the policy, the recipes, the autonomous agents, and then everything that they need to function properly. So templates, custom types, these sorts of things get shipped in cookbooks around to everything. Okay. Recipes and supporting files. Types. Types are super, super, super easy to make in Chef. So I'm going to make a Yum cookbook that has no recipes in it. It's only going to ship a custom type. Okay. So here we are. So we have the interface defined in the resources directory, and then we have the actual implementation defined in the providers directory. Right? So if you remember back in the bash script, I said interface and implementation. The interface was the top where I'm dealing with the variables and the arguments and everything. Dress up like a programming language for Halloween. So interface, very good. I'm saying my Yum repository. It's going to have like repository ID, enable GPG check, true or false, these sorts of things, and defining this thing. So I can list my intentions at the top. I want this Yum repository created or deleted, and then the parameters that I need to make it all work down here. Pretty easy. And then the actual implementation, I'm going to use other Chef resources, right? So I'm going to render a template, Etsy yum repos.d, and then feed it the parameters that I pass in. So here at the top, I'm using this is a special Chef thing, creates a new scope inside of a parameter implementation. It walls off that implementation, right? So we said autonomous agents' inner workings are assumed to be unknown, right here. So new scope. I just so happen to be implementing this with more Chef. I could totally shell out to Bash and do this and be fine. It doesn't care. Honestly, it doesn't care. It's kind of bad. So here we go. I made a Yum type. Boom. Pass my parameters directly into my template. There. Chef. So now we're going to talk about artifacts. You're right, this does get heavy after a while. So, artifacts, right? You need to think about releasing software when you write cookbooks. I don't know why for some case. So once upon a time, in the beginning of Unix, whatever, before we had proper package management and everything, we used this thing called the vendor branch pattern to ship software around. Here's your tarball, right? Then you unpack the thing and you use CVS or whatever, you branch and you compile your things. And then we got enlightened and we discovered packaging, right? For whatever reason, a lot of the config management people want to revert back to the vendor branch model, and I don't know why. Stop. But Chef makes it super easy to actually artifact cookbooks, right? Artifact means you have a written, peer-reviewed, tested piece of software with a version number on it and a well-documented behavior released into the world for your consumption. Okay. So we're going to make an artifact. So Chef cookbooks have metadata, all of them. Super important. It's mandatory. It has a name and a version, right? So I'm going to name this software artifact HTTPD, and it's going to be at version 0.1.0. And I'm going to take my Yum cookbook and I'm going to give it a name and a version and its metadata. It's an artifact. Okay? So this artifact's name is Yum, and its version is 3.0.0. Something we like to do in Chef land is follow a thing called SemVer. It's semantic versioning. It's an English language API about what these numbers mean, basically. So in semantic versioning, we say that the major number, or the top number here, is reserved for major changes. So you can actually break backwards compatibility and break interfaces with a major number. The middle number is reserved for new features, this sorts of thing, and then finally the end number is reserved for bug fixes and patches and things. So if all the software in your ecosystem follows semantic versioning, it's safe to actually only lock down to the first two digits, and you're guaranteed that the last digit is safe to pull in. Unfortunately, not everybody does that, and people that do not follow semantic versioning within a software ecosystem tend to break things. This happens a lot in Rubyville. Sorry. So use semantic versioning, please. Anyway, so to return from that tangent, I'm going to upload my artifact to Chef Server. Right? So Chef Server you can think about as an artifact server. Right? You take your cookbooks and you put them in there, and clients can request them. Right? And since they're artifacts, you can have multiple versions of individual artifacts simultaneously installed on Chef Server. And then Chef Server also handles things for authentication, authorization, and that sort of thing to actually get the artifacts out of the artifact server onto your machine. Delivery. So, in Chef, at first, nodes request their initial run list, and it looks like this, right? So, node, I want to be a web server. Okay, and then it pulls down the HTTPD artifact onto the machine, executes the recipe. Do it. Pretty freaking easy. Then you can do this, add more things to the run list, right? Add more recipes, right? So inside of each one of these recipes is going to be a list of autonomous agents all running on control loops and recurring the system as needed, notifying each other, and all that fun config management stuff. Okay? And then you can kind of do this, right? Just like keep adding things to the run list. Hey, fun. And so for everything, you add like an NTP cookbook, client recipe, it's going to just retrieve the artifact that it needs from Chef server, and then actually compile and execute the client recipe that you've requested inside of it. Cool. Push versus pull. If you prefer push, you're wrong. Pull's always better. There's all sorts of reasons for this, right? Least of which is network considerations. Right? Like so firewalling, those sorts of things. Machines that are down for maintenance. If you have more than like one machine, right? At one point, like one of them is going to be like off, right? Like systems administration is a constant battle with entropy, right? So like motherboards explode. I've seen RAID controllers burst into flames at my house, right? Like this stuff happens. Machines break. They do it often. Hard drives die. Capacitors pop off and go flying across the room. This stuff happens. Right? So machines are going to be down for maintenance. If you're pushing out your policy, machines that are down are going to miss it. So pull, please. And then machines that don't exist yet, right? So you're modifying your cluster, you're adding a web server to a node, you want it to actually pull its policy node. Dependencies. This is where the artifact thing comes in super handy. Right? So we're back at Widget Factory code now, right? So I'm going to make my Widget Factory cookbook here, and I'm going to go in, I'm going to edit the default recipe of the Widget Factory cookbook. So what am I going to do here? I'm going to say, all right, well, I want to include this other recipe, HTTPD server, and then I want to make a Yum repository to access my widgets, because I'm a Widget Factory. I like to put widgets in Yum repositories. And then I'm actually going to install a package. Okay? Well, so I've actually referred to two things that depend on like something else, right? So I have my Widget Factory cookbook. What the hell is a Yum repository? I have no idea. So what I need to do to actually gain access to the Yum repository type is I need to depend on it in its metadata. Okay? So Jeff will actually resolve these dependencies for you. Okay? So you say, I want to run the Widget Factory recipe on the node. It goes, okay. Pulls down the artifact from the artifact server, looks at its metadata, parses it, and says, oh, look at that, dependencies. Let me get those. Right? It does a recursive dependency resolve until you finally get all the things you need, and then you're able to actually run your code. Right? So this, you'll see this a lot in like just normal programming languages because this is programming. Thanks. Integration testing. So I said that artifacts are testable. Cool. So the goal of integration testing is to test to see whether the set of agents has achieved their desired goal. Right? So just because like your config management policy runs and finishes doesn't mean you've actually did what you're trying to do. Right? So you see this kind of stuff a lot in config management, integration testing, LSOF. Like, so check a port, like a curl URL, make sure the machine's actually doing what the policy has intended. Right? Cool. Here's a set of tools. They're all awesome to use them. Right? So Brickshelf's client-side artifact metadata dependency resolver thing that's like built into Kitchen CI now, which is an awesome way to do integration testing at QuickBooks. This comes from the Chef community, but it's going to support other config management types soon. Right now it only supports Chef because it was like Chef people that wrote it, but it was written in such a way that it will soon support Puppet and Ansible and CF Engine and all the things. Okay, pretty cool. And then out of band of the config management tool, very important, it runs the integration tests. Right, so bats and service mapping, those sorts of things. environments. I'm going to zip through this real quick because I only have a few minutes left. Environments constrain cookbook versions, and they allow you to actually set data. Zipping through, so here's an environment. Boom. I want the 1.0 version of the artifact, HTTP artifact. A staging environment, cool. I'm saying I can use the 2.0 version of that artifact. Right? So it gives me a way to actually test the code and install things on a server without blowing things up. Environments can be used to test branches, environments can be used to segregate machines, and environments can be manipulated programmatically. Another chefy thing. Here's an example of me modifying my web server cookbook, right? I'm just gonna change the template thing so that it's looking at some variables. Boom. I can give it a new version, upload it to the artifact server along with some other things that I want, right? And then it exists simultaneously with the output. And then again, I put which factory I run this, and it only pulls down the version that it's pinned to. Okay? Cool. Part 4. Part 4, you're gonna see me talk real quick. So, clusters, right? And this is what we're really all trying to do, right? Is manage groups of machines, right? So far, most of the stuff I've been talking about has kind of been on one machine. But we all know that we have more, so let's talk about this. So here's a typical cluster. This is how I think about clusters in my head, because I do things like that. So I'm going to have different layers, right? So at the top, I'm going to have a load balancer, then I'm going to have a list of a group of machines, like an application server pool, and some database stuff going on down here, right? So there's actually topology between these, right? So IP addresses need to be rendered into configuration files for various services and all this stuff. So you got to actually manage that on top of the actual services themselves. Chef gives you an easy way to actually search out different machines and actually dig out information about them and run them into files, but we're not going to go into that because I don't have time. So check this out. Here's a way to do change management. Right? So I can say production cluster. Cool. This is how I do it. So production cluster, and it's running with an environment set to, I want the 1.0 or 0.1.0 version of the HTTPD cookbook and the 2.3.1 version or something else, whatever. But I'm pinning down my artifact versions in my production environment definition. Okay? So from there, I can actually spin up a entirely mirrored copy of it. So that's doing a disaster recovery test, right? JR testing, very important thing we like to do. But it has the exact same environment. And then my third one, where I actually want to test changes, I want to develop config management code and develop application code and see if it all works. I can spin this up over here, completely separate of everything else, but I update its environment with the new version of the stuff I want to do. Or actually, if I leave it undefined, I just pull the latest. Right? So what I can do then is I can actually update the staging's environment to match that of the development one. And then start running the config management code. Boom. Sometimes it won't take. Sometimes you hit an error and it explodes, right? Well, in that case, you just have to back off and figure out what the hell went wrong, figure it out. And then you do, and then suddenly you can converge the new code onto the existing old infrastructure. Cool. You know it's actually safe to do to production. So you can update your production environment, and then you've just changed. You've managed your change, right? So that's good. Here's an interesting thing. Again, I'm going to zip through here. This is something we all struggle with right now, and you will encounter. So check this out. Here's part of that cluster. I have a load balancer. I have an application server pool, and my application is written in such a way that I need to do the following, right? I need to take a machine out of the pool, drain the connections, modify the configuration, and insert it back into the pool. So what I do is I change my configuration here, change my configuration here, then here, 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 here. And I need to do this in a particular sequence in order to actually make this work, right? How do I do this? Well, here's that ugly over orchestration, right? So in general, there's 3 ways to do this. A conductor showing signals to autonomous agents, So this is basically creative policy manipulation, right? So like on your policy host or chef server, whatever, you're saying, all right, this server doesn't do that, whatever, and you're letting the pull happen and update, and that's hard, right? An external actor controlling sequencing, execution management, so we're falling back like into the land of the monkeys, right? Like we have an external agent like doing gates and phases, like you do this, right, and stuff, and you do that, right? So we have that going on. And then application level sequencing, which is the correct way to do it. Move it up into the application stack, right? So lots of modern applications actually have this built in, right? So things like React and like MongoDB and these sorts of things that can actually like take care of their own ordering considerations without really having to run configuration files. Right? So I guess I'm almost out of time, but so infrastructures are snowflakes, right? Unlike an individual machine inside of an infrastructure, the cluster itself is a snowflake. It is yours, okay? And that's hard because it makes solutions to handle this ordering and orchestration thing, by their very nature, are going to be unique to your snowflake. Okay, so we need to figure out how to do that, and that's kind of an advanced topic. So I guess the things you need to walk away from here remembering is there is no separation between infrastructure and application code. They're the same thing, it's all machines. Distributed systems are hard, and specialists need to work together, right? So like your hardcore Unix sysadmin guy and like your application tier people, they need to get together to figure out how to manage the snowflake properly. That's kind of the essence of DevOps. So do that, talk to your peers. And then there's this, study chemistry, study distributed systems, develop high quality primitives, and ship them as artifacts, and be excellent to each other.
Sorry to cut off. I really enjoyed your talk. It was good to see the similarities and the theory behind it all. If everybody has any questions, we have like 2 minutes left while the next speaker is preparing. So,
Questions?
No, because I have to restart this.
Okay.
So we'll record questions. So, can I give you a signal for when to cut?
You can let as many people in as we let out. So that's 4.
You'll see the Jenkins people going ahead.
Okay.
So,
Okay.
okay. I'm going to try to be back for the Docker talk
Okay.
at 2 here.
Okay.
Hey, Ron. Chef, what do you want me to do on this side?
Okay, so they're done.